Okay, so thank you for the kind invitation and thank you all for coming to listen to these two talks. My first talk is inspired by the fact that last year was not only the centenary of the year of light, but it was also the centenary of the general theory of relativity. To be precise, 25th November 1915 was when Einstein basically gave his theory, and that is the reason we were celebrating the centenary, and we thought that it would be a good idea to expose the excitement of this particular theory with young people like you. So the title first, everybody is afraid of the general theory of relativity. Everybody believes that it's a very elegant theory, but what I want to emphasize is that it's not only beautiful, it's not only deep, but it has passed all possible tests which you can make of this particular theory. So it has succeeded in trying to be, it has been validated by many observations, and eventually we will do astronomy using general theory of relativity. So over my two lectures I will make that particular case. Let me begin with what you learn about gravity in your school almost. The theory begins with Newton's theory of gravity, which was given in 1687. Before that, Newton had already talked about his laws of motion. So when we learn mechanics in school, we learn that mass is a measure of inertia. Mass is also the source of gravity, and there is an inverse square law of universal gravitation, which is the first thing we learn when we are in school and learn about physics. Now if you look at this particular law, of course this law has a very precise expression, but it had very strong philosophical implications. Up till then people believed that the laws which ordinary bodies undergo and the laws which bodies undergo in the heavens, they are not necessarily the same laws. So for the first time Newton showed that bodies on the earth and planets which are in the heavens, they really follow the same laws. So it was a very important philosophical insight into the way the universe works. The next thing is, it was not only a law which was explicitly given like this. Using that law you could predict something and then discover it. For example, by using this particular law, you knew that there had to be another planet. By looking at the orbit of the other planets, for Uranus for example, you could say that a planet had to be there, and they discovered it. So using this particular law, some new discovery was made. So that was a big success, that this law was so good that you could discover something new with this. If you look at this particular law, it also says that the force which you are talking about acts at a distance, and importantly it acts instantaneously. The moment I put this body and this body, immediately there is a force of gravity between these two bodies. That is what this particular law says. So if the interaction is instantaneous, it means the interaction propagates with infinite velocity, because it does not take any time to go from one body to another. Therefore the propagation velocity is infinite. So this is 1687, the first theory which Newton had about the theory of gravity. But in 1905, as Professor mentioned, you had the special theory of relativity, and when you looked at this particular theory, a kind of revolution happened. The first thing is, in addition to gravity, the other interaction which people knew was electromagnetism, and everybody knew the laws of electromagnetism. But just because you had a new theory called special theory of relativity, the laws of electromagnetism did not need to be changed. As they were already consistent with the Lorentz transformations, which is the transformation between two frames which are moving with uniform velocity. It also turned out, when you understood electromagnetism critically, that when we say electric field and magnetic field, they don't have absolute existence. If you are an observer who is moving, the electric field and the magnetic field which you will measure would be different than the electric and magnetic field if an observer is at rest. So you say that electric and magnetic fields are observer dependent decomposition. It is the combined electromagnetic field which has an invariant existence. Similarly, space and time of Newton, you cannot think of them separately. You have to combine and think of them as the object called Minkowski spacetime. So the moment you accepted special theory of relativity, you had these revolutions which were happening. The other important thing when you learn Lorentz transformation is that the speed of light is the limiting speed for all interactions and particles. Nothing physical can move faster than the speed of light. This is again something which happened from the special theory of relativity. So when Einstein in 1907 was writing a review of special theory of relativity, he realized that there was a big tension, because according to Newtonian gravity, the gravity propagates at infinite speed, but according to special relativity, nothing can move faster than light. So therefore he realized that even though Newtonian gravity was a very successful theory for about 200 years, the moment you accepted special theory of relativity, which was only 2 years old, you had a kind of tension between these two theories. One had to be right or the other had to be right. You can't have both of them being right at the same time. So it's like a 2-year-old child, challenging somebody who's 200 years old. This was the basic tension, and in trying to resolve this tension, Einstein finally came with his new theory of gravity. It's a relativistic theory of gravity. That means it's a theory of gravity consistent with the principle of special relativity, and that theory is what is called as the general theory of relativity. This particular theory is considered by almost all physicists as being the epitome or the supreme example of mathematical elegance, conceptual depth. But what I want to emphasize is that it has had tremendous observational success. And as I mentioned, 20th November 2015, we celebrated the centenary of this remarkable theory. With those introductory remarks, this is the plan of what I am going to say later on. I will first tell you how Einstein made this discovery of general theory of relativity, how this discovery was consolidated by observations, how a renaissance happened in this particular theory, and finally, leading on to the second talk, what will be the future of this particular theory. So let's come to the discovery. In 1907, Einstein had what he described as the happiest thought in his life. And this happiest thought, in his own words, is the following: then occurred to me the happiest thought of my life in the following form: the gravitational field has only a relative existence, because for an observer falling freely from the roof of a house, there exists, at least in his immediate surroundings, no gravitational field. If the observer drops some bodies, these remain relative to him in a state of rest or uniform motion, independent of their chemical or physical nature. The observer has the right to interpret his state as at rest. This is exactly nothing else but the kind of examples you do in your 12th standard, where you take a lift and in the lift you put a balance, and in the balance you say that if the lift is accelerated, what is the weight it will read. And the last part of the problem always is, if one of your friends does not like you and he cuts the cable, what will be the reading of the spring balance? And you know the spring balance will read 0. So essentially Einstein is basically saying that if you have a gravitational field which is uniform, but you fall freely in that field, then the gravitational field for you does not exist. So you can see immediately that from a situation where there was a force, you are going to a situation where there is no force. So even though you are looking at physics in an accelerated frame, it looks like it is a situation like you are in an inertial frame. And this, according to Einstein, was the happiest thought in his life, and it has a name. He called it later as the equivalence principle. So now let us understand, why this equivalence principle was very important. And this is what you have to sort of understand, that this was what was unique about Einstein. Remember, what was the problem we were trying to solve? There is special theory of relativity, there is a Newtonian theory of gravity, and we want to make the Newtonian gravity consistent with special theory of relativity. All other physicists only focus on that simple problem. Physicists like Abraham, Nordstrom, etc., they try to take Newton's theory and try to make it consistent with the special theory of relativity. A very mechanical exercise is what they try to do. But Einstein did not attack that particular problem. He actually looked at the physical manifestation of gravity and tried to see, does the theory of gravity which Newton has given us, does it incorporate that physical insight or not? So Einstein was the only person who basically thought that there was something special about gravity which you have to take into account, and only then you would get a good theory of gravity. So this is what I am sort of showing here. If you had an elevator and I look at the following two situations. I am on the earth, only I am not I can assume, for example, that the gravitational field is constant, and in that particular situation I compare two situations. This is actually sitting on the earth, so there is a gravitational field, but if I go to a frame which is accelerated, then in that frame there is no gravity. So you are basically saying that if you have a uniform gravitational field, you can eliminate it by going to a freely falling frame. Now do the other thing. Suppose you have a uniform gravitational field and you go to space where there is no gravitational field, but you go to an accelerated frame. Then what Einstein said is, you can artificially create a gravitational field by going to an accelerated frame. And those of you have seen movies like Interstellar or other science fiction movies, you would see that that's exactly what is done today, that when spacecrafts go up, if people would be sort of floating freely, but then when you start letting it spin, you can create an artificial gravity, and then it looks as if you are standing on the surface of the earth. So Einstein's basic point was that the gravitational field has this remarkable property, and if you therefore construct a theory of gravity which does not take into account this important fact, then your theory of gravity is incomplete. So what Einstein argued was that by a mechanical experiment you cannot distinguish between a uniformly accelerated frame and a uniform gravitational field, and if you ask why is this happening, let's compare it with what happens in electromagnetism. Suppose you have an electric field, and in that electric field suppose you put a body of charge q, then you know that the acceleration which the body will pick up, it will be given by the ratio of charge to mass, because q into E will be the force, m is the inertia, so q E upon m will be the acceleration. So all bodies will not fall with the same acceleration in an electric field, because q by m for all bodies is different. But suppose you are in a gravitational field, I told you that mass is a source of gravity, mass is also a measure of inertia. So if you try to write the same equation for gravity, you will find that you will get the ratio of what is called as the gravitational mass to inertial mass. And even Newton knew that these are not actually the same things, and Newton is supposed to have done a lot of experiments. You can do the simple exercise, try to do the problem of the period of a simple pendulum, and keep careful difference between what is the gravitational mass and what is the inertial mass, and then you will find that the period of the pendulum really depends on this ratio of these particular bodies. So if you make a pendulum made of uranium and take another pendulum made up of lead, you will have that mg upon mi for uranium and mg upon mi of lead. But if the period is the same, it means for all materials this ratio is a universal constant. So Einstein argued that this important fact which nature is telling us, if you don't build it into your theory of gravity, then your theory of gravity cannot be complete. And this was basically Einstein's insight. If you remember, Einstein's special theory of relativity generalizes from Galilean relativity by saying not only the laws of mechanics have to be the same for all inertial observers, all the laws of physics have to be the same for all inertial observers. Here he argued that not only mechanical experiments, you do whatever physics experiment you want, you will not be able to distinguish between the accelerated frame and the presence of a gravitational field. And that is really the equivalence principle of Einstein, and therefore the statement which you can make is, do any experiment in a freely falling lab over sufficiently small time, it will give results which are indistinguishable from those if you do the same experiments in an inertial frame in empty space. This basically was Einstein's insight, and was very special to Einstein. No other physicist basically thought that this is the key to understanding the theory of gravity. This is the reason we say that any other physicist may have discovered special theory of relativity, but general theory of relativity could only be discovered by Einstein, because it was only Einstein who had this physical insight about this particular behavior of gravitation. And then, as I will show you in my next slide, the moment you accept this, there are some insights which follow, and there are some very explicit consequences which you can derive, which he used to build his general theory of relativity. So the first thing is that if you have a gravitational field, and in the gravitational field you let some light move, there has to be a change in frequency or wavelength when light falls in a gravitational field. Now, the way he argued it is very simple. He said, let's take a body, let it fall in a gravitational field. When it falls, convert it into sort of photons or light, let the light go up, and if the when you fall in a gravitational field, the photon does not change its frequency, then you can construct a perpetual motion machine by this particular process. So it basically says that a gravitational field affects the propagation of photons, and therefore it means that if you look at the frequency of light, the inverse of frequency is time. So you can use this to construct clocks or to measure time. So it means that in the presence of gravity, time is affected. If I am on the ground and if I am on a mountain 1 kilometer high, my clocks will not run at the same rates. So this is one important point which he said, and then people try to do experiments with sun and white dwarfs to look for this particular effect, but because of the fact that doing these spectroscopic experiments have a lot of uncertainties, you could really not verify it very easily. So this is one very important consequence which Einstein had, which is just discovered just by looking at what happens when light propagates in a gravitational field. The next thing which he talked about was the fact that if there is light propagating in a gravitational field, then light should bend. Now, the way he argued it is very interesting. He said, let us look at the propagation of light in an accelerated frame. We know that if you look at a propagation of light in an inertial frame, light should propagate in a straight line. But you try to do the same calculation, what happens to the propagation of light when you look at an accelerated frame, and then you will find that because you are looking at this problem in the accelerated frame, you would get a parabola for the propagation of light in this accelerated frame. Then he argued that whatever happens in an accelerated frame must also happen in a real gravitational field, and therefore in the presence of a gravitational field, light should bend. So the moment you accept the equivalence principle, you can derive how much bending of light will happen. He calculated that, and it turns out that it is a very small number. The deflection is 0.875 seconds of arc, and he realized that if you can do an observation of starlight during an eclipse, maybe you can measure it. And he tried to convince one of the German astronomers to try to do these experiments. Unfortunately, the World War I started immediately at this particular time, and therefore this experiment was aborted. But in retrospect, he was very fortunate, because as we will see later, this number is only half the effect. When you really look at the full theory, this number is not the complete story, and therefore if this experiment was done at that particular time, he would have probably been not as successful. So the important point is that looking at what happens in an accelerated frame gave him insight about the theory of gravity itself. This is one kind of accelerated frame. Another kind of accelerated frame which you can talk about is a disk which is sort of rotating. A lift is linear acceleration, but if you have a rotating disk, a rotating frame is an accelerated frame of another kind. Now, when you look at a rotating frame, again something very remarkable happens. What he argued was that suppose you take a rotating frame and then you do the following measurement. Try to make a measurement of the circumference and try to make a measurement of the radius, and take the ratio of them, because the pi really is the ratio of circumference to the diameter. Now, if you try to measure the circumference, because of the fact that there is velocity in that particular direction, there will be length contraction. So your rods would be contracted when you measure the circumference, but the rods along the radius, because it is perpendicular to the velocity, will not be contracted. So if you had the ratio of circumference to the diameter or the radius in a rotating frame, the answer would not be equal to pi. But we know that if you really had the ordinary geometry which we learn in school, that answer should always be equal to pi. So he again argued that because this happens in an accelerated frame, in the presence of a gravitational field also, the geometry would not be the geometry of Minkowski spacetime, but something more complicated, and that is what we call as a non-Euclidean geometry, a geometry which is not flat, but a geometry which could be curved. So again, you can see that by these two arguments, Einstein slowly is coming to the conclusion that the spacetime, Minkowski spacetime, which we talked about when we learned special theory of relativity, is not the correct description if you take into account the theory of gravity. You have to modify spacetime itself if gravity exists, if you want to describe gravity. And that is why if you learn about popular books, you really learn that when you talk about the general theory of relativity, we have to talk about curved spacetime. So you can see that the simple physical arguments really led him there. And this is of course the kind of picture we talk about, that you should not describe gravity as a force, you should just describe gravity as describing the geometry of space-time itself. And if you ask a mathematician, how do you describe geometry, he will tell you that there is a mathematical quantity called curvature or distortion, and if you describe the curvature or distortion, then you can describe the geometry, and once you describe geometry, it is actually a description of the gravitational field. So this is how Einstein basically came to his theory of gravitation, and therefore starting from 1907, by all these physical arguments, by 1912 he has realized that the way forward is to combine the gravitational field and the space-time structure into something which we can call the inertio-gravitational field, because if you did that, then the remarkable equality of inertial and gravitational mass is automatically inbuilt into this theory. Because remember, how did we say that space-time is curved? We use the equivalence principle. Why is the equivalence principle there? Basically because of the fact that the inertial mass and the gravitational mass, that ratio is a universal constant. So his basic point was that if you built this geometric theory of the gravitational field, then immediately this experimental fact is automatically built into this particular theory, and that is exactly what he did. So you can say that Einstein's unique and enduring legacy is the insight that space-time and gravity should be described by the same structure, and because you have equivalence principle, space-time could not be flat, it had to be curved. And if you learn your little tensor analysis, you normally know that geometry is described by the metric tensor. So Einstein's insight was that the gravitational field will be described not by a simple scalar potential, but by a second rank tensor field, which is the metric of this particular space-time. So the whole point is that instead of just having one equation, remember, if you have Newtonian gravity, you write down the Laplace equation or the Poisson equation for the scalar potential, which is phi. What Einstein basically said was, what really describes gravity is this tensor field, which is the metric. So instead of having one equation, you have 10 equations, and this is really the complication which you have. Remember, we always think Einstein was very mathematical minded, he understood mathematics and so on, but it was really not the case. He used to bunk his mathematics classes. So when he came to this particular point, he realized that whatever he had done by bunking those classes, now he was paying for it. So he talks to his friend, who was a mathematician called Grossman, and he tells him that you must help me, otherwise I'll go crazy, because I don't know how to deal with these 10 equations finally. And therefore what really happened was that after 1912, with his friend Marcel Grossman, he had a collaboration. Grossman was a mathematician, and he knew how to describe curved space-time, because there was this great work by people like Gauss, Riemann, Ricci, Levi-Civita, etc. So he provided for Einstein the mathematics which was required to formulate his general theory of relativity. And therefore, now this is a slightly technical slide, don't worry about it. The reason I am putting this basic slide is to tell you that what really happened after 1912 is that Einstein worked with his mathematician friend and came up with theories of gravity which were different from general theory of relativity. So he came with his first version of this theory with Einstein, with Grossman, and there were technical problems with this particular theory. But the important point is that even though eventually we will see that this was a wrong theory, what the historian of science basically argue is that this really was something like a scaffold which he already had built, so that when he gave his final theory in 1915, he had already built the framework on which a new theory could be built. So the important point is that these wrong theories were also very important because they laid the framework for what we could do very efficiently much later. Here another important, good friend called Michel Bessot, and with him he again worked on some aspects of the gravitation theory, because remember I told you that according to him the rotating disk was like a gravitational field. So if he had his theory of gravity, the rotating disk should be a good solution of those equations. So he worked with his friend to verify whether it was really a solution of those particular equations. But again, you can take heart when you make mistakes, that in 1915 he discovered that even though they thought it was the correct solution, there was a mistake in their calculation. So don't be under the impression that geniuses like Einstein don't make mistakes. They make mistakes, but the difference is that when they find that mistake, they know how to correct it. They don't stick to their original hypothesis because they made it. They correct it, and that is what you really have to learn, how efficiently to correct the mistakes which you make when you start out with doing something like that. And then something which Einstein sort of realized, that all this mathematics is okay, but if he is going to come up with a theory of gravity which is different from Newton, it should have some prediction which Newton's theory does not have. And that he worked with his friend, because there was a problem in astronomy where Newton's gravity did not have the right result. This problem is related to what is called as the motion of the perihelion of Mercury, and what he did with Bessot was used his incorrect theory to calculate the correction to Newtonian theory. Why is this an interesting thing? So let me try to explain. When you learn your classical mechanics course, you basically learn that if you have planets, they move in elliptical orbits, right? So the orbit is a closed orbit. But if you really look at the orbits of planets like Mercury, it's not a closed orbit. It is a rosette. It is an open, orbit which keeps switching more and more. So the whole question is Kepler wrong or something else is the problem? And then you sort of realize that when we learn about planetary motion, we think that there is the sun and the planet. But in the actual solar system, there are other planets also which will act on the planet. So there will be perturbations, or there will be corrections to the motion because of other planets, and therefore it's not a simple two-body system, but a two-body system which is perturbed because of the gravitational effects of other planets. So this great astronomer Bala Iyer during the years 1843 to 1859, when he studied the orbit of Mercury, he pointed out that there is a problem in understanding the motion of this planet. The orbit is not an ellipse, and he could measure it, and the observations of this particular thing were measured for almost about a century, and then the point which was made was that this observation, the amount of shifting which it has is a very small amount. It is 574 seconds of arc per century. In 100 years it moves a small amount which is given by this. Now you can see again here the astronomers were very sure about their observations, but the important point is mathematicians could calculate what will be the effect of other planets. So the following was the audit. When you did the audit, because of Venus you could say that this was the amount of precision you should have, because of Jupiter it must be so much, because of Earth it should be so much, because of the rest of the planets at most about 10 degrees. You add that up and you end up with 531 seconds of arc. So if you look at your observations, they should only give you 531 seconds of arc, but what was the observation? It was 574 seconds of arc. So there is a 43 seconds of arc which is missing. But both the people who calculated it and the people who observed were very confident about this particular number. So Bala Iyer said that there is a problem, because if you believe Newtonian gravity, there is this missing 43 seconds of arc. What Einstein was hoping was that because his theory of gravity was different from Newton's theory of gravity, maybe it will have additional contributions, and that additional contribution would explain this 43 seconds of arc. But when he actually did the calculation, he found that it gave only 18 seconds of arc. So it is very clear that his theory is giving something, but not enough, not complete to give this 43 seconds of arc. So you can see that when you try to construct a new theory, it is very important to come up with a physical prediction which is different from what was there before, and this is exactly what Einstein was ready to do. So in 1913, Einstein has this a theory which is sort of not very satisfactory, and at that time Planck visits him. Einstein is living in Zurich at that particular time, and when Planck asks him, what are you working on, he tells him, I am trying to come up with a new geometric theory of gravity. And Planck tells him, as an older friend, I must advise you against it, for in the first place you will not succeed, and even if you succeed, no one will believe you. But Einstein did not listen to Planck. He believed that he was on the right track, and therefore in 1915 he again goes back to look at his equations, and as I told you, he discovers that he has made a mistake in his work with Besso, and therefore he had to modify whatever Lagrangian he started out with, and then he realizes to do that he has to change his definition of the gravitational field, and when he did that by doing what we do today, he basically comes up with what we call as the correct theory of gravity. The state of his mind during that particular year, in the beginning of that year, is well described by this person, Dennis Overby, who writes popular articles on science. So it's a very nice description, so I just wanted to share it with you. By the fall of 1915, Albert Einstein was a bit grumpy, and why not? Cheered on by his disgust by most of his Berlin colleagues, Germany had started a ruinous world war. Einstein was always against war, but many of his colleagues felt that Germany should go to war with the rest of Europe. He was living alone because he had separated from his wife, and his friend basically said he sleeps until he is awakened, he stays awake until he is told to go to bed, he will go hungry until he is given something to eat, and then he eats until he is stopped. So his mental state was not very good because he was really worried about his theory of gravity, and worse, he had discovered a fatal flaw in his new theory of gravity, which was propounded with Grossman a couple of years earlier. And then, of course, like every other scientist, he no longer had the field to himself, because the very famous German mathematician David Hilbert also was breathing down his neck, because when Einstein goes to Göttingen, because Hilbert invited him to give a talk, he tells him about his theory of gravity, and because it's a theory which had interesting mathematics, Hilbert wants to start working on this particular theory. And then Einstein becomes very insecure because he knows Hilbert is stronger in mathematics than him, and he becomes very, very insecure, and therefore over 4 Thursdays in November 1915, he writes 4 short papers on 4th, 11th, 18th and 25th, and finally on 25th November he comes up with what we call today as the general theory of relativity. And the important point which I told you is that he could really do this over 4 weeks, not because he really figured out everything in these 4 weeks, it's basically because over the last few years he had already set up the framework. So it is like the historian of science describes it very nicely. He said that earlier he set up this particular scaffold. On that scaffold he put tiles of a particular kind, but then he realized the tiles were not very good. The framework was good. So he takes out those tiles and puts the right tiles, and that becomes the general theory of relativity. So that is really how they call this particular discovery. They say it is the scaffold and the arch. What we see today is this magnificent arch which we call general theory of relativity, but it was really built on all his joint work with his mathematician friends like Grossman, Besso, etc., etc. And I think that this is one of the important things which has come out, because during the centenary, historians of science have gone back, looked at Einstein's papers and discovered, and therefore this picture which we have of Einstein being a lone genius who discovered something sitting in his room is not the correct picture. He collaborated, took inputs, and therefore it also tells you what the importance is of discussing physics with colleagues around you. So essentially, as I told you, in November 2015, he basically comes up with this particular theory, and this particular theory is what we call today as Einstein's equations. It basically tells you that this combination of the Ricci tensor, which is called as the Einstein tensor, should be determined by the energy momentum tensor, which is the T mu nu of space-time. So these are the basic Einstein's equations, and after he discovers it, he writes to the famous physicist Sommerfeld, during the last month I experienced one of the most exciting and most exacting times of my life, true enough also one of the most successful. Now the marvelous thing which I experienced was the fact that not only did Newton's theory result as the first approximation, but also the perihelion of Mercury, which is 43 seconds of arc per century, as the second approximation. So remember, when you learn the special theory of relativity, when you look at the equations of mechanics, etc., you have the leading term, which is the Newtonian term, and then you have corrections of v square by c square, v4 by c4, etc., etc. So when you look at Einstein's theory of relativity, general relativity, in the leading approximation it should always give you Newton's theory, because otherwise you lose all the success of Newtonian theory. But then, because of the fact that it's a relativistic theory, it has to have corrections. So there will be v square by c square, v4 by c4, these kind of corrections, and those corrections are what will give you this extra 43 seconds of arc. So Einstein's theory really succeeded in describing what the observers had seen in 1856, that there was a discrepancy in the planetary motion, and that planetary motion discrepancy was explained by Einstein's theory of relativity. So one slide summary of what is general relativity. So we can say general relativity is the best description of gravitation. It unifies special relativity and Newton's law of universal gravitation, and describes gravity as a geometric property of space-time. The curvature or distortion of space-time is directly related to the energy momentum tensor of matter and radiation, and the relationship between them is what we call as the Einstein field equations. Just as we have Maxwell's equations for electromagnetism, we have Einstein's field equations for general relativity. Unlike Maxwell's equations, which are linear, this system of equation is very complicated. It's a system of 10 non-linear partial differential equations. Philosophically also there was a big change. Remember, when you looked at special theory of relativity, there was Minkowski space-time, and in Minkowski space-time you had things which were sort of moving. But what happens in the case of gravity? We said that it is no longer the Minkowski space-time. The space-time itself is getting affected because of the presence of matter, because matter creates gravitational field. So in a sense, space-time is not like this stage which I have here, but it is more like a situation where fields are there. In the original picture of special relativity, fields are just actors, but in this particular case, space-time itself, because it describes gravity, has become part of the characters themselves. The way I try to visualize always is that if you look at this picture called matrix, you would basically see that geometric structures are no longer rigid. It just keeps sort of fluidly changing as matter keeps sort of moving around. So that is really Einstein's picture of space-time itself. Matter and radiation, when they sort of move, they will distort or they will make space-time change, and therefore gravity in some sense manifests as the distortion of geometry itself. So you basically say that if you have space-time, it is matter which tells how space-time should curve, and once you have space-time, it is going to tell matter how it should sort of basically move. So this is this consistent picture which Einstein had, that gravity is not a force, but gravity is space-time itself. Now you may basically sort of wonder that on the one hand I am telling you that by going to a different frame I can remove gravitational field. Then what is gravitational field at all, right? Because I have told you that gravitation does not have a physical existence. I can always go to a frame, it's a frame dependent effect. In some frame it is there, in some other frame it is not there. So what is really the true nature of gravity? So you have to remember that when I was formulating my equivalence principle, I used the word uniform. So if there is a uniform field, you can transform it away. But a real field is not uniform. There is a gradient in that particular field. So what is shown here is that if you have a real gravitational field, and in that gravitational field, suppose you take two bodies, if they had a certain separation, in a real gravitational field, because the force on this is going to be more than the force on this, this separation will change with time. Why is the separation changing? The separation is changing because there is a gradient in the gravitational field. The field is no longer uniform. Similarly, if I take two objects which are separated in this direction, again because both of them will fall towards the center of the earth, this separation again, instead of being this large one, will again become small. Why is this happening? It's again happening because there is a gradient, or there is the the tidal effect of this particular gravitational field. So the important point you have to keep in mind is the uniform part of the gravitational field can be transformed away, but the tidal fields cannot be transformed away, and that is what represents the physical effect of gravitational fields. So this is the last slide which I want to share with you, and that brings me to the next part of the talk. We have this particular theory, and now Einstein, what will he try to do? He will try to do all possible calculations, predict something, and try to do an experiment to verify it. So he goes back and tries to calculate in his new theory what is the deflection of light. Is it the same as 0.875 or is it different? So he does this calculation, and he finds that if you take his new theory, the answer is double that answer. It is 1.75. Now it's very easy to understand physically why that is so. In the earlier case, the gravity was assumed to be Newtonian. He was using the equivalence principle. So in a sense, he was calculating what the deflection is relative to straight lines locally. But when you are doing an actual physical problem, the star is somewhere else, you are very, very far away from it. What you call straight lines near the star and what you call straight lines far away are not really the same, because the space-time which you are talking about is not a flat space-time but a curved space-time. So if you try to take into account the separation of how the local straight lines bend relative to straight lines far away, there is an additional contribution which comes into the theory, and adding them together you totally get this 1.75 seconds of arc. Now it is very interesting that the answer to this part really depends on the theory of gravity. If you don't have general theory of relativity but you have another theory of gravity, this number can be very different, and therefore by verifying this particular number you can also verify whether Einstein's theory of gravity is the correct theory, or you need to modify even Einstein's theory of gravity. He makes this particular prediction, but by that particular time, remember, the World War is happening, 1919, it's almost the end of the World War, and at that particular time there is this British astronomer called Eddington who proposes that he would like to go and verify this particular result. And it was very interesting, especially comparing with the world in which we live in today, that you have a scientist called Eddington. He does not want to join the war because he believes that it is against his religious principles. So he protests and doesn't want to go to war, and says that I really want to go and verify this particular prediction of a scientist who's really a German. So the British and Germans were fighting this particular war, but it is amazing that during that particular time this was really possible. Even though two countries were at war, there were a few people who allowed him to not only not go to war, They also allowed him to verify a theory which was given by an enemy scientist. And then when it was sort of discovered that it really was true, then of course all the newspapers essentially went berserk, and this is exactly the kind of headlines. All the newspapers in the world went on, and you can see that Newton was the British scientist, Einstein is a German scientist, but the newspapers don't care. So this basically said that in this climate of war, science was the big unifier, and after that Einstein and general theory of relativity really became overnight sensations, and Einstein's aura has not abated since then. When all this happened, somebody went and asked Einstein, you became very famous because of this, but suppose the observations did not confirm what you had predicted, what would you say? Then Einstein was humorously said that I would have been sorry for the God, because I know that my theory is correct. So he was very, very confident. So remember, this was Einstein. It's not that he always did the correct things, but once he came to the correct result, he was always sure that that is the final word. His confidence finally was big and amazing. So things are bent, and because things are bent, if you use your optics, knowledge of optics, there should be effects like lensing and so on, and we know that in astronomy effects called gravitational lensing do exist, and this has really become a very important area by which we can understand, make observations about the universe. It tells us a lot of things. So something which Einstein came up with, that light is bent by gravitational fields, has become a big area of research which is called gravitational sort of lensing. So you can see, you may have thought 0.87 seconds of arc, 1.75 seconds of arc. What use is it going to be? 50 years from then, it has become a big area of research. The other thing, as I told you, was gravitational redshift. Gravitational redshift was predicted, but it was such a small effect that you could not really verify it. But in 1960, because of the fact that technology had become much more sensitive, these scientists, Pound and Rebka, basically demonstrated by 1965 that gravitational redshift should really happen. And their experiment really became possible because of the fact that this experiment, which is called the Harvard Tower experiment, there was a big tower, and in the tower the gravitational field, because on the top of the tower and the bottom of the tower has a small difference, and therefore if you send radiation from one side to the bottom or from bottom to the top, because if there is a gravitational redshift, then something should happen, and because of the fact that you had techniques like the Mossbauer effect, you could really verify that gravitational redshift indeed happens. And in the Nobel citation of Mossbauer, the fact that this experiment can be done by using Mossbauer effect indeed finds mention. So you can see that again a small effect, because of the fact that there is a very sensitive experiment which you can do, now you can have verification of the redshift effect. Something remarkable happened afterwards, and again this is something which we should all be aware of. Remember, one important revolution already had happened in astronomy. Astronomy till the Second World War was basically optical astronomy, but during the Second World War, physicists discovered that you could use radio waves for radar detection of planes and so on. So when the war got over, they basically realized that all those techniques which they had used could be used to do astronomy, and that was the birth of radio astronomy. And the picture of the universe which we had from radio astronomy was very, very different from the picture we have about the universe in optical astronomy. Radio astronomy basically tells us the universe is not a quiet place. It consists of a large number of violent events. So in connection with the general theory of relativity, also something remarkable happened, because what happened after the Second World War was that the Americans and the Soviets basically started exploring space travel, and in doing that, for getting to accuracy required for space travel, they basically started doing tracking of planets so that you could send spaceships to other planets. So basically you had interplanetary space programs, and as I said, to do that they started radar ranging to planets and satellites. Now because the distances involved are much larger, small effects started playing a very important role. So you can't just use simple Newtonian propagation of light to calculate how much time the radiation will take to reach the planet and come back. All the relativistic effects had to be folded in this particular calculation. Also you had to measure things much more accurately, and new technologies like the use of hydrogen maser, atomic clocks, radio interferometry techniques for quasars, space platforms where you could do experiments, all these started becoming available to the people doing fundamental physics, and therefore you realize that something which was happening on the political front started affecting the theory of relativity. Again, David Kaiser, who was one of the scientists involved in policy making, basically writes, physicists and engineers working on enormous radar arrays to detect incoming Soviet missiles calibrated and fine-tuned new system by sending radar pulses to the nearby planets. They realized that if they timed the return echo from planets with accuracy, they could test a subtle prediction of Einstein's general theory of relativity. Gravity slows the speed of light as well as bending its path. For decades, this delay provided the most precise measurements available that space-time behaved exactly as Einstein predicted. So he basically says even the most abstract scientific research can be buffeted, derailed, and even propelled by the most potent force of all, which is politics. So you can basically see that the motivation really comes from politics, from military requirements. And the effect which we are talking about is what is called as the Shapiro time delay. So basically, if you try to do radar ranging, when you have light going close to the sun, you will find that if you take a round trip to Mars, for example, it takes about 42 minutes, but then there is a small effect because of this Shapiro time delay, which is about 200 microseconds. But since you can measure things very accurately, you can try to find whether this 200 microseconds is indeed correct or not. Again, as I explained last time, half the effect comes from equivalence principle, but half comes from the curvature of space-time, which depends on the theory of gravity. So the correctness of this number of 200 microseconds is a test of Einstein's general theory of relativity. What is shown in this simulation is the following, that if you are sending light from Earth to Mars, depending on how close the light goes to the sun, the delay can be as small as 70, or as you can see, it is going down because you are far away from the sun. But as you get closer to the sun, that number will start going up. And you can monitor this. And this is basically because of the Shapiro time delay. So the important point is that you could start making these sensitive experiments which verify Einstein's general theory of relativity. Since I am running out of time, I won't talk about this. There is another important effect which Einstein's theory predicts. It predicts that just as in the case of electricity, if you have a pure electric field, if you go to a moving frame, it will be a combination of electric field and magnetic fields. In Einstein's theory also the same thing happens. If you have a pure electric gravitational field, if you go to a rotating frame, it has effects which are analogous to the magnetic field, and that is what is called as gravimagnetism. And this gravimagnetism is a smaller effect, just like magnetic effects are always smaller compared to the electric effects, but there was a very sensitive experiments which could prove that Einstein's prediction of these magnetic effects are indeed very close to what Einstein basically predicted. I'll end by sort of saying that I'm talking about spacecraft, I'm talking about things which are done in astronomy. Is there any use of general theory of relativity in our daily life? And I would say yes, all of you are using general theory of relativity anytime you buy a smartphone, basically because of the fact that in your smartphone many times there is a GPS. And what is really the GPS? The GPS basically consists of transferring time between a system of satellites, 24 satellites which the Americans have put up, which have atomic clocks running in them. They are all synchronized with clocks running on the Earth, and by transferring time from one of these satellites to a satellite on the Earth, you can calibrate your location on the Earth very, very accurately. But because of the fact that these satellites are moving, there have to be special relativistic corrections between a clock on the Earth and the clock on the satellite. Because they are at different gravitational fields, time runs at different rates, so there have to be general relativistic corrections. So if you don't correct for these two things, your GPS will not basically work. So anytime you use the GPS in your smartphone, you basically are using the special theory of relativity and the general theory of relativity. And remember, if you have been following the newspapers, more recently the ISRO has launched something called the IRNSS, because of the fact that we would like to have our own GPS, because we know that the Americans will not share with us the most accurate data which is available to them. And if you really want to track things for military, you really need much more accuracy than what is available to civilians, and therefore we have started the process of constructing our own GPS, which is called the IRNSS. So the important point is, general theory of relativity is not only an abstract theory, it is something which affects our daily lives. In the last few minutes, I just want to go back to the, this part. I'm going to be much more faster, so don't, you can ask me questions later. There is something which happened later on which led to the birth of, which led to a renaissance of general theory of relativity, and this basically comes from astrophysics. In addition to ordinary stars like the sun, at some particular point in 1930s, people realized that stars can be very, very compact. They can be completely made of neutrons. They could be as massive as the sun, but the radius could be of the order of a few kilometers, about 10 kilometers. Now these stars are made up of pure neutrons. So you can think of this as being a giant nucleus. It's a 10-kilometer long nucleus, and because of the fact that it is a very compact object, the gravitational field on this is very, very strong. Nobody knew how to discover this particular object, but nature provided us with a big surprise, because in 1967, Jocelyn Bell, who was a graduate student, discovered, when she was trying to do some other experiment, trying to do radio scintillation experiments, observations of something which had remarkable periodicity. It was almost as if somewhere in the heaven there was somebody sitting there with a flashlight and sending you signals at a very precise rate. So people tried to interpret these signals which were coming with exact periodicity, and since this period was a very, very small number, it turned out that they could not be ordinary stars. They had to be very compact stars. So from these pulsars, you inferred that these pulsars should really be rotating neutron stars. How can you have a neutron star which will be like a pulsar? It is exactly like your searchlight on a circus. If you go to a lighthouse, how do you see the beam of this lighthouse? There is a light there. That light points towards you, but because it is sort of rotating, after some time again you get this. So if you have a light which is stuck up on a body, and if that body rotates, you would get pulses, and that pulse tells you how much is the period of that particular rotation. So from reconstructing this period of this particular object, people could know that it had to be a very, very compact object, and they basically discovered neutron stars. So the important point I want to sort of tell you is that in this previous theoretical prediction, this object should exist. Nobody knew how to look for it, but in nature, while doing some other observations, an observation gave us the existence of objects called neutron stars. Are there objects with more compact gravitational fields? It turns out that again theoretically people knew that there can be objects like black holes. Black holes are supposed to be objects whose gravity is so strong that if light tries to escape it, it cannot escape it. Remember, if you have this earth and from the earth you want to launch a satellite, the way you do it is you calculate the escape velocity from the surface of the earth, and then if you exceed that escape velocity, then the object will actually go away. So you do the same kind of argument. It is a heuristic argument. You can argue that if an object has a very strong gravitational field, then from that there may be situations where light would not be able to escape, and these objects were called black holes. Now black holes were studied theoretically for many years. It really is a big subject of research in general theory of relativity. Some aspects involve advanced mathematics more than the mathematics you normally learn in colleges and so on, but the important point is that it was believed to be only an experimental idea. But then a few years later people discovered the existence of objects called quasars, and when you try to explain the energy output of quasars, again people realized that you cannot construct this by ordinary physical forces. It had to be really associated with strong gravitational fields which are associated with black holes, and this basically led to the birth of the subject which we today call the relativistic astrophysics. That is, the application of general theory of relativity to astrophysics becomes an important area of research. To this area many scientists of Indian origin like Chandrasekhar, Vishweshwara sort of contributed, and it is a very active area of research even today. The other important application of general theory of relativity is to explain the advanced, the structure of the universe itself. General relativity allows you to explain the first 3 minutes of the birth of the universe, and again I just want to rapidly go over it. As I told you, one of the important things about general theory of Newtonian gravity was that it told us that the laws on the earth and the laws in the heavens, that means the solar system, were really the same. Einstein argued that the theory of general theory of relativity could not only be applied to the solar system, it could also be applied to the full universe. And when he tried to do that, immediately he discovered that his equations were predicting that the universe could not be a static universe. The universe had to be either expanding or it had to be contracting. At that time everybody believed, because of observations, that the universe was actually a static object. It was not a dynamic object. So Einstein thought that maybe his theory was giving him wrong predictions, and he basically tried to say that if I believe my general theory of relativity, it is going to lead to a dynamic universe. So maybe there is another force which repels, which is repulsive, which balances the gravitational force of attraction, and therefore there is a static situation and there is a static universe. And that is why he introduced what we call today as the cosmological constant problem. He introduced something called the cosmological constant, but unfortunately in a few years Hubble discovered that the universe is actually expanding. And then of course we have this whole picture about the expanding universe. But the important thing again I want to emphasize is that theory has many predictions, but it's only when you make an important observation you can distinguish one theory from the other. And then once the expansion of the universe really started, people like Gamow basically said that if the universe is really going to be expanding, maybe there must be some primordial radiation in this particular universe. People tried to explain the synthesis of elements we see in the universe, how elements are synthesized in the stars in the beginning of the universe, etc., which is called the Big Bang nucleosynthesis. And then again at that particular time people like Hoyle, Narlikar came up with another theory which basically said the Big Bang theory is not a nice theory because it has some singularity. Maybe the universe is really described by a steady state theory. So there was a period when there was a big conflict between whether the universe is a steady state or whether the universe is really a dynamic Big Bang. Again, because of the fact that even if you have a very beautiful theory, the steady state theory is more beautiful because it does not have singularities. But the point, as I want to emphasize, is that it's the final word is always given not by beauty but by observations. And once again in 1965, the cosmic microwave background radiation was discovered by these people, and the moment you did that, this beautiful theory goes out of the window, and today we believe that there is a universe, and the black body radiation which exists in this particular universe, we can characterize it by a lot of observations which came from satellites like Kobe, WMAC, Planck, etc. So not only we have a black body radiation, we also know the properties of this black body radiation. We also know, for example, today that the universe is not constantly expanding. There is something very mysterious called the dark energy, and we can say that even though there are many things which we don't know, we have a standard model of the universe which tells us what the universe did in its first 3 minutes. So you can see the success of this particular theory. Not only it tells you about stars, it also tells you about the beginning and end of this particular universe. The last part which I am going to talk about in the next lecture in the afternoon is about gravitational waves. I will tell you how they tell us about the last 3 minutes of objects like black holes and neutron stars, and how when you go beyond detection, we will basically discover a new astronomy, and how the LIGO-India project can contribute to it. So this part of the lecture will come back later. I just want to say that there are many things about gravity which we know, but even today we don't have what we call as the quantum theory of a gravity. A lot of people, brilliant people like Weinberg, Feynman, etc., really tried to construct a quantum theory of gravity, but even today we don't have a good way. There are many proposals for quantum theory of gravity, but we don't have a quantum theory of gravity. And if you ask why don't we have a quantum theory of gravity, again the answer is that we really don't have observations or experiments. So what I want to stress in this particular theory is that theoretically many things are possible, but finally you really need inputs from physics. Only then you really have a good theory of gravity. So we are 100 years away from the discovery of general theory of relativity. I hope I have convinced you that it is not only mathematically elegant, not only is it conceptually deep, but it has had amazing observational successes over the century. If you look at research today, it has a lot of mathematical sophistication. It has a lot of exchanges with many advanced mathematical areas, numerical computations, high energy physics, the emerging area of gravitational wave astronomy, and all this is basically possible because of exchanges or progress which have happened in technology and experimental techniques which have become much more precise. So the point is that after 100 years Einstein seems to be right, but the question which we always want to ask of any particular theory is it 100% right? Remember, Newton's theory was a right theory for almost 200 years, but then later on it had to be changed. Same thing happened in neutrino physics. We always thought neutrino was massless, but you know the Nobel Prize last year was given to a discovery that neutrinos are not massless. So the important point, I hope I have convinced you, is that if you want to understand the universe, you really have to learn general theory of relativity, because only by using that you can really understand the universe in which you live in. So with that, I basically end with Einstein himself. Einstein seems to have been a very popular figure, because you can see that if you look at the cover page of Time, even in 1922 he was called man of the 19th centuries. When there was a year of physics, again you saw Einstein was there. In 1999, during the centennial, he was voted the person of the century. So Einstein seems to be timeless in some sense, and if you really look at the science he created, you always would realize that it was unique. His insight was always sort of unique, but personally he always connected with the world around him, and he had an opinion about the world which he lived in. He had opinions about Gandhi, about Tagore, about Charlie Chaplin, he had an opinion about the world. All of us who aspire to be scientists always want to be Einstein. Sidney Harris basically said that if the Earth is destroyed, if you want to put a tombstone for it, the tombstone should say Einstein lived here. So you can see that he is held in a kind of esteem which none of us can ever aspire for. But what I want to emphasize is that not only in his science, but in all the complex human endeavors, Einstein always told us the following. One important thing is that you cannot solve problems with the same thinking by which you create problems. So if you start with a problem, if you want to solve it, you have to really go beyond the problem itself. And the other important thing he always told you is that something may be true for 200 years, but it does not mean you should stop questioning it. So the most important message to students is never stop questioning whatever is told to you in your class. So question me. Thank you.